Your robot is just a collection of parts until you tell its motors what to do. Getting your motors to spin correctly is the first major step in building that robot that can actually score points and win matches. This is a fundamental skill, and in this video, I'm going to give you a complete step-by-step guide to controlling a DC motor in Java for FTC Robotics. My name is Coach Pratt, and I've been teaching robotics and design for over 10 years. And in that time, I've coached national champion FTC teams, and those teams have won multiple Inspire Awards. I've seen students in your shoes just getting started with Java, and I know how to coach you through from start to finish. So today, I'm going to walk you through the entire process. We'll start with the physical wiring and setting up of your robot's configuration file. Then we'll jump into the code, organizing it properly with its own class. And finally, we'll run through several practical examples from simple spinning and reading encoders to making your motor react to sensors or gamepad movements. By the end of this, you'll have a working motor that you coded yourself. If you have already set up your programming test bench and you've been following along with the series and the playlist, you can go ahead and skip right to the code section. If you don't have this set up, let's go ahead and set up your configuration file. First thing we do is we make sure we wire our motor here. This is a Go Build a Yellow Jacket motor, but you can also use a REV motor just fine. And it runs straight from our bullet connectors out of the end of the motor here. And I've plugged into motor port 0. I've also gone ahead and plugged in the encoder because we're also going to get a chance to use the encoder on the motor today. Now, the encoder is effectively just a rotary encoder that just keeps track of the number of ticks and the number of times that a motor has rotated. So as this spins, you can keep track of just how far along its path that it has gone. Now, the motors in here are relative encoders. They are not absolute encoders, which means that when you repower your robot, the encoder itself resets back to 0. So in order to tell our control hub what is actually connected to the device, we have to make what's called a configuration file. So I'm going to go ahead and click these 3 dots up here. I'm going to come into Configure Robot. And let's actually go ahead and zoom in so we can see that a little better. I already have a test bench 1 set up, so I'm going to go click Edit, or you can make a new one, doesn't matter. And I'm going to tap on my Control Hub portal, my Control Hub, and I'm going to tap on Motors. Next to our motors at port 0, I have a Go Build a 5202/4 series, I believe it's 5204. So select the correct motor that you have connected to this and then give it a name. I'm just going to name my motor, but you would probably give this a little more accurate one, like a linear slide motor left or linear slide motor 0, whatever that is. I would suggest you write this as snake case or underscores between any new words you have, just to keep with some proper naming conventions. We'll go ahead and we'll go back out of here. Now that we're done, we'll go ahead and click Save, give it a configuration name. And then in order to activate this, we're going to click Activate. It's going to disconnect our robot and restart it really quick, just to let it know that, hey, this is the current hardware that you have connected to your device. So with your self all initialized now we can head on over to Android Studio and actually get started with programming. Looking at our code, if you've been following along with my tutorials up to this point, you can go ahead and continue to add all the code we're about to add into our test bench class inside of our mechanisms package. If you have no idea of what I just talked about, don't worry about it. We're going to go through this again. So inside of our team code, I like to have a separate package for all of the hardware or the mechanisms that are attached inside of our robot. If you don't want to do that, you can right-click, select New, make a new package, and call it Mechanism. Inside of our Mechanisms folder, we're going to create a class called Test Bench. If you have gotten up to speed, all this code we're about to add, you can add it into your current test bench file, but I'm going to make a new class here called Test Bench 1, just for the sake of making this tutorial a little bit easier to read if the only thing you want to learn about is how to use the DC motors. So inside of a public class Test Bench 1, we're going to create a new private member variable, and this private member variable is going to be called motor. It is going to be of the DC motor class, and we're going to call it motor. Now, in your case, you could probably call this something a bit more clear, something like a linear slide motor 0. Should be something more obvious, or actually, sorry, that wouldn't be lowercase. So linear slide motor 0 or linear slide motor 1 or linear slide motor left, whatever have you, it should be more descriptive of what your actual object is. But because we're just doing this on a test bench for this tutorial, I'm just going to call it motor. Now, inside our mechanisms, we have some sort of initialization statement so that we can pull this object into our OpMode class. So I'm going to make a public void, and I'm going to call this one init. You can call this anything you want, but because we're already using an init statement inside of our OpModes, I'll continue to call it here. And we're going to give it a hardware map with a hardware map as an argument. And inside of this, for those who've been following along, where you had your previous touch sensor code, you could leave the touch sensor code here. And then down below, we're going to add in our DC motor section. So for a DC motor, we're going to assign our motor is equal to hardware map.get. We're going to set it to the DC motor.class, comma, and then you need to give it the exact name that you did in your configuration file. In this case, I called mine motor, but yours might be linear_slide_1. Whatever it is that you chose, but it has to match the name on your configuration file exactly, or it won't work. Then it's time to actually set the mode of your motor. So I'm going to go to motor.setMode, and there are several different run type modes that you can use. So I'm going to grab DC motor.runMode. There are 4 types of modes you can use. You can run using encoder, run to position, run without encoder, and stop and reset encoder. So run to position works if you have an encoder attached to your robot. And what it's going to try to do is it's going to try to run to the encoder tick that you have selected. So if you remember on that DC motor, inside of it, it has a encoder written inside, and it's basically a rotary encoder. So let's imagine, just for simple of math, that each one full rotation of this wheel is 100 ticks. So you could set it to 500, and it's going to attempt to rotate this thing 5 times. Run using encoder is going to try to run it to the targeted speed that you set. So whatever the velocity that you've chosen, let's say you want it to run at full 1 speed power. It's going to try to use that encoder to make sure that the motor is running at that targeted velocity. The run without encoder is just going to run at whatever velocity that you've set it at. Let's say you set it at 100% power or 50% power. It's going to attempt to run at that 50% power, but it's not going to be able to verify if it actually is running at that speed or not. And then that stop and reset coder does exactly as you expect. It stops and resets the current encoder value. So we are going to choose run using encoder so that we can set it at target velocity, and it will attempt to reach that 50% speed, 100% speed, whatever it is, using the encoder. And it uses some of its built-in PID to attempt to upgrade its power or boost up its power until it reaches that targeted velocity that you selected. Now, the reason I'm using this run using encoder mode is because if you have 2 motors that are running with each other and they're combined, this has the best chance for both of those motors to run at the exact same speed over any of the other modes that exist. And what I mean by that is, let's say you have your drivetrain and you have 2 of them set up on, you have a motor on your left and motor on your right, and you're trying to run yourself forward, saying run using encoder. If they're both running at 0.5% velocity, it will attempt to do its own internal PID to be able to move those motors at the targeted velocity that you choose, and you have the greatest chance of your robot actually moving straight instead of moving to one side because one motor is overpowering the other motor. And that being said, there's nothing wrong with using run to position on DC motor if it's just going to be a single motor constraint. However, I really recommend against using run to position for anything like a drivetrain or a dual motor setup, because it's possible that your motors will end up getting out of sync and fighting against each other. You may also find that on a drivetrain, if you have 4 motors that are all trying to run a position, that your motors get a little bit wiggly or jittery as it goes around, because they're all attempting to run themselves to a specific encoder position as opposed to trying to match the speed between each other. And the reason I suggest that is because when you set up your drivetrain or your chassis, it's really hard to confirm that our 4 wheels have the exact same amount of friction and forces applied to them. You may have tightened a bolt harder on one of them. You may have a slightly looser belt on one of yours, that it makes it a lot more consistent for your drive motors to be able to move if you use a run using encoder. So now at this point, we have to actually create a setter method. Because we're going to be using this class in a separate op mode, we have to be able to access the hardware objects that are inside of this class. So we're going to make a new public void, and this is going to be a setter method. We are going to say set motor. And we could say even set motor speed to be a little bit more descriptive. And it's going to take a double speed as its parameter. Can't find my acrylic brackets today. And then there's going to be no return type. We're simply going to grab our motor dot set power, and we're going to set power with our speed. And then just as leaving some trails of breadcrumbs for ourselves, this accepts values from negative 1.0 all the way up through 1.0. So any double in between those values. So let's go ahead and actually test running our motor. So inside of our new team code section, we're going to right click and make a new class. And we're going to call this class DC Motor Practice. And our DC Motor Practice is going to extend the OpMode class. And in our OpMode, we always need two methods. If you remember, we need a public void init, and we need a public void loop. So I always put in those just to get started. So the first thing we need to do is we need to create a new instance of our actual hardware. So I'm going to grab test bench 1 because this is the testing bench 1 that I've been using. You may have test bench without a 1. With the bench name is going to be equal to a new test bench 1. And inside of our initializer statement, we need to run that initialize method that is inside of our test bench 1 class. So I'm going to go to grab bench.init, and it requires us to call in a hardware map so that we can actually keep track of where all this specific hardware is. So whenever we press the init button on our driver station, it should actually start running this up. Now for our loop, we're simply just going to run our motor at 0.5% speed. So we're going to grab bench.set motor speed, and we're just going to call this with 0.5. So now if I were to build this code, I'm going to make sure that I have the REV Control Hub 1 connected. And I also want to make sure that my control hub is connected to my computer using a USB-C to USB-A cable. All right, so let's go ahead and actually run our OpMode. Oops, I made a mistake over on our desktop. Did it again. I forgot to write in at teleop or at autonomous. And if you don't have this, it won't actually show up in your driver station. Some of you probably noticed that as I was going through my tutorial and say, hey, Coach Pratt, you missed that. So let's go ahead and build this and we'll get back to it. All right, so let's go ahead and grab our teleop, our DC motor practice. We're going to init, and that's actually going to set all of our hardware. And now as soon as I click this play, we should have our motor actually running at 50% speed. And congrats, you've actually got a motor running. Let's do a little bit more fun with this motor. Now your motor, as I was talking about earlier, had an encoder inside of it. You can actually read that encoder to be able to do some work with it. So I can go back to our test bench class. Oops, I closed it down. And inside, we're going to create a new private double ticks per rev, or ticks per revolution. So for a single revolution, we're going to be able to keep track of the number of ticks. And when we initialize this, we need to actually set it up with a value. So in our init method, we're going to actually go ahead and assign this a value. So we're going to say that our ticks per rev is equal to motor dot get motor type dot get ticks per rev, or get ticks per revolution. Now, similarly to our motor speed, we could set our ticks per revolution, but we actually don't want to set what the current encoder is at this point. We only want to be able to read that. So I'm going to say a public double, we'll call it get motor revs. At this point, the only thing we have to do inside of this get function is return motor dot get current position divided by our ticks per rev. So the reason we have to divide this by ticks per rev is that if we just got the current position, all we would do is we would just get the current number of ticks. But rather we want to divide it by the number of ticks in a revolution so we can put this into some sort of meaningful normalized value. So this is basically normalizing ticks to revolutions. Now, if you have a gear ratio set up your motor, you're going to have to calculate this in as well. Now, let's say, for example, you had a 2-to-1 gear ratio. In order to calculate that, all you'd have to just simply multiply this by 2 so that you are accounting for that double reduction in the number of revolutions that you have. Now, I'm not going to do that in this case because we are just using a standard motor inside of the test bench, so I'm not going to render that confusing. Heading back to our DC motor class, we should be able to actually grab in our number of motor revolutions. So we're going to, inside of our loop, we're going to say telemetry dot add data. We're going to add in the motor revs, and then we're going to grab our bench dot get motor revs method. So let's go ahead and run this on our control hub and see what that looks like. So let's go ahead and grab our tele up. If we run this, we should notice that if we look at our driver hub, we are now starting to count up. If your motor revolutions is actually counting down, that means you've likely wired in your motor backwards. Not necessarily backward, because the DC motor does allow you to do that, but you have likely changed your polarity on your DC motor. I'm going to go ahead and stop this. So let's do a little bit more fun with DC motors. We can actually change our brake modes and things like that. But in order to get a little more practice with programming, we're going to change our brake mode by using the touch sensor on our board here. So on my configuration file, I have a touch sensor that's wired into port digital 2.3, and it is called touch_sensor. If you've been following along my tutorials up at this point, inside your test bench section, you should have your, let's actually open it up. You should have your touch sensor object as well as your get state functions, and we're going to use these in the next section. I would suggest you pause it on the screen right now if you don't have this all inside the same class, since you can add your test bench sections for this DC motor as well as your getter and set methods into your testbench.java. So because this hardware map can get out of hand really, really quick, I like to make sure that I'm adding in little code comments. So I can say that where inside my init statement I'm doing my touch sensor, where inside my init statement I'm doing my DC motor, as well as where inside of that hardware class I have my touch sensor, getter and setter methods, as well as my DC motor, getter and setter methods. So what we want to do is we want to inside our main loop, if we're pressing our touch sensor, we want the motor to run. Otherwise, or else, we want our motor to stop. So nice thing is, because we have this all inside of our main test bench Java, it keeps our code super clean inside that init statement. And here we're going to say if then, parentheses, bench.is touch sensor pressed, we're going to set that motor speed to 0.5. Else, we're going to have bench.set motor speed to 0.0. And this stops the motor when you set something at 0. And then we're simply going to say what our current motor revs are. So let's go ahead and compile this, build it, and then put it onto our robot controller to see what that looks like. So let's go ahead and run this tele up. So now it's not being run until I press and hold the touch sensor, at which point it starts running. When I stop, it stops. Now you'll notice that the motor itself is floating. So when I stop this, it doesn't automatically hard stop itself. We can actually set that as a parameter inside of our code. So let's come back to our desktop and we'll go back into that testbench.java. And there are two other methods that we can use to be able to set up our motor. So what I can do is I can say motor.set zero power behavior. And in this zero power behavior, we've got dc.zero power behavior dot break or float. What break does is when you stop that motor, it attempts to actually break or stop it. Float means that it just cuts power and it will still continue to be able to roll and float until it rolls up to a stop. So I'm going to go ahead and select break. One more that you could do at this point is if you have your motors set up in reverse, as is pretty typical for mechanism drive, there's two ways you can do that. You can either swap the polarity on DC motors, or you can go ahead and do motor.set direction, and then DC motor dot direction dot forward or reverse. So now because I've set this up as reverse, it should actually reverse our motor and it should break as well. So let's go ahead and run this. Nice thing is, because that is a separate class, we don't actually change any of the code inside of that DC motor practice method or class. So now compiled here, so we can go ahead and grab this. And now when I grab this, you'll notice that rather than floating, it automatically stops all by itself. Now, of course, you don't have to just use a touch sensor to be running your motor. You can also use something like a gamepad. So for instance, inside of our loop, what I could do as I could make a new double called motor speed. And I can set this to gamepad 1 dot left stick Y. And then for our set motor speed, I'm actually just go ahead and remove these if statements. And I can simply do something like bench dot set motor speed, and we'll just give it with the value of motor speed. So now, if I were to be using a gamepad, we know that this gamepad returns 1 and -1. I can actually just be controlling the speed of that motor just directly off of the analog joystick itself. So that's a whole bunch of information on using DC motors. And now let's get into some practical examples and exercises for you to try out. Do not skip these exercises because they are the best way of solidifying your knowledge of actually using DC motors. It's all fun and good to just walk through with me on this, but if you're not actually trying it yourself, you're not actually ingraining that learning. So let's go ahead and actually do some exercises here. So exercise number 1, I want you to add a method on your test bench that allows you to change the brake behavior from your OpMode. So on A pressed, oops, I cannot spell today, set brake. On B pressed, set float. So I would suggest you pause the video now and try to sort that out yourself. So a lot of ways you could do this. Let's take a look at how I would do it. Inside of the testbench.java, we're going to go ahead and add a new method to our DC motor section. And we are going to call this a public void, and we're going to call this one set motor 0 behavior. And we're going to pass in one parameter. It could be our DC motor dot 0 power behavior. And we're going to call this one just 0 behavior as our method. As our variable. The only thing we're going to do is we're going to say motor dot set 0 power behavior. And we're going to call this one with 0 behavior, which is that parameter we just put in here. Then on our DC motor practice, inside of our main loop, above our telemetry section, I'm going to write an if statement. I'm going to say if gamepad1.a, that means if gamepad1.a was pressed, we are going to call our bench dot set motor 0 behavior, and we'll call it with DC motor dot 0 power behavior dot brake. And then else if gamepad1.b is pressed. Oops, I cannot type my curly brackets today. We're going to grab our bench dot set 0 power behavior again with our DC motor dot 0 power behavior dot float. Again, I love that autocomplete because remembering what all of these methods are, you will forget all the time, and having that Android Studio makes it so simple. The reason I did not make this a if-else or a if-if is because really you'd only want one of them to be able to be true at a time. So that's how I've decided to go about doing it. I hope you found that a helpful quick tutorial in using DC motors inside of your FTC REV Control Hub. If you ran into any problems, if things didn't make sense, let me know in the comments down below, and I'll do my best to try to help you out to get your robot up and running. Other than that, you can check a link in the description for more FTC tutorials. There's also a link to a fantastic book by Alan Smith. His are where a good chunk of this tutorial came from for using these DC motors, and it's great for doing a little bit of extra reading on furthering developing your skills inside of FTC Robotics. So best of luck this season, and good luck out there on your next robotics project.